monatomic gas. But since it is unstable, like he was saying, it always exists in the two atoms. If you are talking about the individual level, if we are talking about the water, obviously in the case of the water, it exists like H2O, but in the case of the single gas, it exists like O2. Okay, so monatomic gases are single atomic gases such as helium, neon, or argon. अच्छा, अब क्या है कि हम अज्यूम करेंगे कि why we need basically हमने assume तो नहीं किया, actually we have taken the monatomic gas. So why we have taken the monatomic gas? ठीक है, the question is कि why we need monatomic gas, why we are not talking about the diatomic gases. So the reason is कि internal energy of the monatomic gas consists of only of the translational kinetic energy. There are no rotational kinetic energy associated with the monatomic gas. It is it is not a part of your course, but according to the quantum theory, when you are talking about the monatomic gases, they only have the translational kinetic energy. But when you will deal with the diatomic gases, you will also deal with the rotational kinetic energy. So in order to make our calculations quite simpler, we usually take the monatomic gas, okay, then we make certain assumptions, and after that we calculate the equation, and then afterwards, if you are, we calculate a relation, okay. So in this case, in order to avoid the tedious calculations, we are assuming that we have the monatomic gas and that its an internal energy is only the sum of translational energies, kinetic energies, rather than the rotational kinetic energy. So the average kinetic energy of every single atom. Okay, if I will ask you, okay, you have a gas which is at 30 Kelvin, and you have a gas, you have the atoms which are at 100 Kelvin. So whose molecule will have higher kinetic energy? What do you think?
100 degrees centigrade.
Obviously 100, because kinetic energy is directly dependent upon the temperature of the system. Okay, so greater is the temperature, greater would be the kinetic energy. Okay, so in that case, the kinetic energy is directly dependent, average kinetic energy is directly dependent upon the temperature, and the relation, just hold on a second, beta. A second. Just, yeah. And the relation that basically deals with it is this one. This shows that the average kinetic energy is directly proportional to the temperature. K is the constant. Here it is the gas constant. मतलब K and R over Na होता है. ठीक है. Previously we have assumed that K is equal to R over Na in the first lecture of this chapter. ठीक है. So obviously it is a constant because R is the gas constant, N is the Avogadro number. So K will be constant, 3 over 2 is the constant. So the only thing that is varying here, or on which the average kinetic energy is dependent, is the temperature. So we can say that the average kinetic energy is directly proportional to the temperature as per this relation. Okay? So कहते हैं, let's suppose if you have a n mole of a gas, okay? So the atoms, we have taken the monatomic gas. So if we have n mole of the gas, the total number of atoms would be equal to n into the Avogadro number, because we do know that 1 mole of a gas contains 6.023 into 10 power 23 atoms. So if you have n mole of gases, so obviously it will be equal to n into 6.02 into 10 power 23. Okay? So n 6.02 into 10 power 23 is basically the Avogadro number. So they have written it as n into Na if you have a n mole of the gases. So then the kinetic energy will be equal to, एक second beta. Just a second. Okay, then the kinetic energy will be equal to what? एक second. बेटा फिर कोई ना कोई admit हो रहा होता है. Here you can see that obviously the total internal energy will be equal to total translational or the average kinetic energy of each atom. So it will be like this one. So the total number of atoms is given by this relation n into Avogadro number. Okay? So this would be the total internal energy. We do know that average kinetic energy is 3 by 2 kT. Okay, so we just put the value of average kinetic energy. So this relation, and we have, so this relation will be equal to what? 3 by 2 n into na kt. We also know that, as earlier I was saying, k, okay, k is r over na. So we have just put the value of just for एक सेकंड बेटा, मैं ये लिख दूं ताकि कैलकुलेशंस में आपको थोड़ा सा प्रॉब्लम here. This question can be written as n into na 3 by 2. आगे क्या आएगा बेटा? ऑब्वियसली ब्रैकेट के अंदर क्या आ जाएगा? r by na into t. So this na will cancel out. ठीक है, the end result which you will get here in this case, ये this na will cancel out with this one. So the end result you will get will be equal to internal energy is equal to 3 by 2 nRT. So again, from this equation we can see that this is for the monoatomic ideal gas. Okay, so any gas मतलब can be ideal as long as their density is very low. ठीक है, और means that the collisions between them
excuse me sir.
जी जी
सर वो इक्वेशन वापस लिख सकते हैं
बेटा? just आपने the above equation you have just put the value of the k here. ठीक है, so just ये वाली equation you just put the value of k in this equation, and thus you have cancelled out na by na, and it would be equal to obviously 3 by 2 nRT. Okay, so here again from this equation you can see that the internal energy is directly dependent upon the temperature, because R here is the gas constant, as N is the number of the moles, and 3 by 2 is obviously a numerical value. Okay, so it is internal energy is directly proportional to the temperature here. Okay, so up to this point clear?
Yes sir.
Okay. So in the next here in this statement, he just basically explained this equation that the internal energy of an ideal gas is a function of the gas temperature only. It does not depend upon any other variable. Okay, it means that greater is the temperature, greater would be the kinetic energy. Smaller is the temperature, smaller would be the kinetic energy. There is no any other variable involved in the kinetic energy of the or the internal energy of the gas here. Okay, so in the next case example, he has basically given the two stages. Okay, in this case, okay, there are, this one is the first one here. This is the initial stage here. This one is the initial, and this one is the final stage here. Okay, so from I to F, okay, two processes can take place. Okay, from I to F, if you are dealing with the constant volume process, अच्छा नहीं, बल्कि ये next में है. ठीक है, ये नहीं अभी आप करें, ये next के साथ है, constant volume के साथ. मैं आगे आपको explain करता हूँ. ठीक है, so here in this case कहता है कि we will drive using this internal energy, we will be able to drive an expression for the molar specific heat of an ideal gas, and there will be basically, as I told you earlier, that there will be basically two equations, one for the constant volume process and the other would be for the constant pressure process, because we cannot take temperature constant here because we are taking the temperature as a variable for the internal energy here for this case. Okay, so in first case we will take the volume constant as he is saying, and in the second case we will take the pressure constant. So one by one we will deal with both of them, and then we will find out or drive their equations, and then afterwards there will be a sample problem related to these molar specific heats of the ideal gas. Okay, So here he's saying molar specific heat. First, we will drive the relation for the molar specific heat at constant volume. So for that purpose, he is saying that you have a gas confined in a container, okay, which has a fixed volume. How it has a fixed volume? Because he is saying there is a pin from this end and there is a pin from this end, which is basically uh, uh, which basically stops the expansion of the volume here. Okay, so from the thermal reservoir, which is at high temperature, a small quantity of heat is entering into the system here. So it means that the temperature of the gas is rising. So when the temperature of the gas rises, obviously one is the pressure of a gas will also rise here. So this process can be explained graphically by this figure 19.9b. Here, this is the first one, initial stage, and this is the final stage. Okay, so at initial stage, the system has a volume V and pressure P, and there was a temperature T. So temperature T of the gas. So when small amount of heat is transferred to the gas, what happened that since the volume is the constant, so the pressure of the gas increased because temperature is increased by a factor delta T. Okay, so this process goes from this stage, from I stage to F stage, and at F stage you can see that the pressure is increased by a factor delta P and the temperature is increased by the factor delta T, while the volume of the system remained constant. So in order to explain, or if I want to represent the data graphically for the above figure, so this figure basically shows me the process at a constant volume. So is this clear? Any question about this figure? Okay.
सर थोड़ा फिर बताइए प्लीज
क्या आपने पूछते हैं
सर इस फिगर के बारे में
आप पूछे, मैं बताता हूँ
सर मेरा मतलब है शुरू से एक्सप्लेन कर सकते हैं इसको
नहीं, शुरू से क्यों आप करना बेटा? आप क्वेश्चन पूछे, इट मींस के इट इज जस्ट लाइक यार आप लोग, मुझे तो समटाइम्स ये लगता है कि यू आर ट्राइंग टू जस्ट
सर साथ साथ पॉइंट्स लिख रहे होते हैं तो वो जो कह रहे थे वो मिस हो जाता है
sometimes मतलब मुझे it seems कि you are trying to shorten the course, के मतलब आप छोटा करना चाह रहे हैं कि जितने मर्जी के क्वेश्चन पूछ लें, क्योंकि कोई रेलेवेंट चीज कोई ऐसा नजर नहीं आती कि पूरे का पूरा मैंने रिपीट करना है, वो तो मैं कर दूंगा, लेकिन मुझे जो तंग कर रही है चीज वो ये तंग कर रही है कि कोर्स आउटलाइन आपकी कवर नहीं होनी इन 2 लेक्चर्स में जिस तरह आप सली से बैठे हुए हैं। तो फिर सेकंड यही है कि आई विल इंक्रीज योर लेक्चर्स from the if I will see that I am not able to cover the course, so I will obviously increase your lectures per week. Okay, so just keep in mind the process here in this case is because it is just repetition of your old processes which we have studied, isoporic process, isobaric process, adiabatic process. So you can see that it can be considered as a isoporic process, because in this case what we are doing is basically we are keeping the volume constant. So when heat enters from the reservoir to the gas, so it will only increase its temperature. Okay, so at the initial stage the temperature was T, volume was V, and the pressure was P. So when the heat enters into the system, so since volume is the constant, it will remain same. So what will happen that it goes from volume goes from state I to F, and it will remain same, it will not change. Okay, and then the only thing that is changing here due to the absorbance of the heat from the reservoir is the temperature. The temperature at initial stage will be T, so after absorbance of heat it will be transfer from T plus to delta T, like this one here. Okay, and the pressure again it will also change at the F final stage. It will be P plus delta P, means that there was a rise of the pressure of delta P. So this is the overall process that he has explained here. Okay.
Yes.
So overall, up to this point, they have written all this theory. Okay. So then he said that we find that heat is related to the temperature by this relation. Okay, like when we calculated the specific heats, okay, and the heat capacity, we studied these relations. So this relation will be equal to this heat is that is absorbed by the gas can be written as like this one, where Q क्या है आपके पास heat absorbed है या transferred हुई है to the system, and N is the number of the moles, ठीक है, CV is the constant molar specific heat constant at constant volume, and delta T is the temperature. Okay, so we will use the first law of thermodynamics that is given by this relation. This is the first law of thermodynamics, that the internal energy is basically equal to Q minus W. So Q is given by this relation, while W, obviously no work is done by the system or on the system. So how does I know this? Because we have taken the volume constant. So obviously there was no expansion or no compression. So I will take W equal to 0. So this overall relation will become something like this, because by putting the 0 in this equation, W will be negated out. So from this equation, I can rewrite CV would be equal to the internal energy divided by M delta T, which is given by here. And in the last scenario, we calculated the internal energy, which was equal to 3 by 2 NR delta T. So I will put this value, okay, up to this point. So again, CV was equal to 3 by 2 R. एक second बेटा. Just जी जी.
Q heat added या released है?
बेटा आप अगर टेम्परेचर इंक्रीज कर रहे हैं, सो इट मींस हीट इज अब्सॉर्ब्ड बाय द गैस, ठीक है, rather than रिलीज करने के हीट इज अब्सॉर्ब्ड बाय द गैस हेयर. अगर टेम्परेचर डिक्रीज होता या प्रेशर डिक्रीज होता, then obviously it means that heat is released by the system. Okay, so this relation is equal to, so the question is substituting this results into this relation. When I will put 3 by 2 nr delta T in this relation, delta T will be cancelled out, ठीक है, small n will be cancelled out. The only thing that will left behind will be equal to 3 by 2 R. Okay, so this will be the relation, ठीक है. CV would be equal to this one. एक second. So क्या होगा कि this we can generalize the overall equation for the internal energy NCV here. अब ये relation कैसे आई? How this equation came by? ये इक्वेशन कैसे
को CV से रिप्लेस कर दिया?
बिल्कुल. In the equation 1942 3 by 2 R क्या होगी कि आपके पास इक्वल किसके आ रही है हमारे पास CV के. So we will just put the value of CV here. So the overall internal energy, the total internal energy will be equal to this one. ठीक है. There we were taking the temperature, मतलब a small amount of temperature was changing. So overall, in order to write the total internal energy of the monoatomic gas, ठीक है, as the constant volume, so the relation would be equal to this one. ठीक हो गया? Up to this one clear हो गया? Any question?
सर ये मोनोटोमिक के लिए तो वो ऊपर वाली थी, ये आइडियल गैस के लिए दोबारा बताइएगा कि किस तरह हुई है.
मोनोएटॉमिक भी बेसिकली आइडियल गैस ही अज्यूम कर रहे हैं बेटा हम लोग, ठीक है. गैस कोई भी हम लोग डील कर रहे हैं, वी आर डीलिंग विद आइडियल गैस, ठीक है. मोनोएटॉमिक से ये मुराद था कि व्हेन वी वर टेकिंग दैट वैल्यू, तो उस वक्त हम लोग ये कर रहे थे कि उसको हमने आइडियली किया हुआ था कंसिडर, ठीक है, लेकिन जस्ट ये कंसिडर किया था मोनोटॉमिक था, ठीक है। तो अगर आप यहाँ पे देखेंगे, यहाँ पे फॉर द डायटॉमिक गैस आपके पास जो रिलेशन आएगी दैट वुड बी इक्वल टू 5/2R, और जो मोनोटॉमिक के लिए आएगी वो 3/2R आएगी, ठीक है। इसमें उन्होंने नीचे लिखा हुआ भी है, दिस क्वेश्चन नॉट ओनली अप्लाई टू एन आइडियल मोनोटॉमिक गैस बट आल्सो टू द डायटॉमिक एंड पॉलीएटॉमिक आइडियल गैसेस प्रोवाइडेड, मींस के कंडीशन क्या है कि अप्रोप्रिएट वैल्यू ऑफ
Yes, sir,
CV
ऊपर
should
लिखा
be used, ठीक है। So CV here in this case for the monoatomic is 3/2R, while for the diatomic it would be equal to 5/2R, and for the polyatomic gases it will be equal to 3R. ठीक है, क्लियर हो गया बेटा?
जी सर।
सर ये जो
चलो।
क्वेश्चन 19.44 है सर, ये इसका बता सकते हैं सर कि ये कैसे आई, क्योंकि 19.43 तक समझ आ गई, आगे समझ नहीं है क्या हुआ।
आगे जस्ट आइए बेटा, यू विल जस्ट पुट द वैल्यू ऑफ 3/2R। क्या है 3/2R की वैल्यू आपके पास यहाँ पे बेटा? 3/2R की वैल्यू ये है आपके पास CV, so you will just do के 3/2 and into R it would be equal to what NCV delta T. So when you will write in a generalized form, मतलब when you temperature change जो है मतलब स्मॉल हो रहा है तो ठीक है, आप ये इक्वेशन लिखेंगे 1945, लेकिन अगर आपके पास टेम्परेचर चेंज नहीं है, फिक्स टेम्परेचर पे आप ये डील कर रहे हैं तो टोटल एनर्जी आपकी इसके बराबर होगी। क्लियर हो गया?
यस,
आपने जस्ट CV की वैल्यू इन इक्वेशन 1942 में पुट की है, कुछ भी मजीद नहीं किया आपने। ठीक हो गया?
यस सर।
चलें, गुड। सो अब आपके पास क्या है कि अब ये इक्वेशन क्या कहती है? कहती है कि चेंज इन द इंटरनल एनर्जी ऑफ ए कन्फाइंड आइडियल गैस डिपेंड्स ओनली ऑन द चेंज इन द टेम्परेचर। मतलब आप अर्लियर भी हमने ये बात की थी कि इंटरनल एनर्जी ऑफ द गैस इट ओनली डिपेंड्स ऑन द टेम्परेचर, ठीक है। अब इन द लेफ्ट हैंड साइड पे जो तीन उसने ग्राफिकल फिगर्स दिए, सॉरी बेटा, and he followed 3 different paths, ठीक है। In first path he is using the constant volume which we are just discussed. In the second path he used the process of constant pressure. In the third path no heat enters or leaves the system, adiabatic process की बात की है। तो अगर आप लोग इन तीनों में देखेंगे तो फाइनल स्टेज में आपके पास only thing that is varying here on which the internal energy is dependent is the temperature, ठीक है। all 3F or the final stage is lying on the same plane if you are dealing with the same amount of the temperature or heat. If you are giving same amount of the heat to the gas, they will all lie on the same line, ठीक है, same process, and it shows that it is only the total internal energy is only dependent upon the change in the temperature, ठीक है। So in this case he basically explained this phenomena। ठीक हो गया बेटा? ये देखें, ये उसने लिखा हुआ भी है, change in the internal energy is the same for all 3 paths। चलो अब आ जाते हैं हम लोग टुवर्ड एट कांस्टेंट प्रेशर। टाइम खत्म तो नहीं होने वाला बेटा?
सर जी 5 मिनट रहते हैं।
5 मिनट रहते हैं सर।
फिर मेरा कि दोबारा ज्वाइन कर लें आप लोग, ताकि जो है बीच में ना रह जाए, फिर दोबारा, ठीक है, कंटिन्यूटी रहे। ठीक है, मैं आपको मतलब एंड करने लगा हूँ मीटिंग, तो आप काइंडली दोबारा ज्वाइन करें।